Hello. Today in Applied Calculus, we're going to learn about implicit differentiation. It's going to be an application of the chain rule, so that's why we learn it right after the chain rule. So for most functions, we have seen they have been in an explicit form. An explicit form is where we have y equals. And so with something like 4x squared plus 5x minus 3, we have y equals, and so we can just take the derivative. And you may not think about it, but what you're doing is taking the derivative of both sides, and when you write y prime or dy dx, that was you taking the derivative of the left-hand side, and then of course you knew that you were actively having to take the derivative of the right-hand side with the x's. But there are some functions that are only implied by an equation. They're written in an implicit form. So something like x times y equals 1. Well, I could solve that. So if we have xy equals 1, I could solve that for y to put it in an explicit form. And so now we have y equals, and then I could go ahead and take the derivative. Okay, but the issue that we're going to encounter is that sometimes just doing this rewriting to get it to our normal y equals is either very difficult or even impossible. So if I had something like x cubed minus 2y squared plus 3y equals 2, with y's located in multiple places and to different powers, again, it would either be very difficult or beyond our level right now, or sometimes really impossible to get it in a nice form. So that's why sometimes we need to use something called implicit differentiation, where we don't rewrite it as y equals, we don't even try, and we take the derivative implicitly. So when we're taking that derivative implicitly, we're not going to get y by itself on one side. The function's going to have y's mixed in with it, and we're going to have to remember that chain rule. So even though we don't know what y is equal to, y is equal to something, and so whenever we take its derivative, we have to remember there was an inside function. We have to multiply by the derivative of the inside. And so it really is us applying the chain rule when we do that. So let's take a look. So if I want to take a derivative of an x, nothing is going to change. And the notation is going to become even more important. Notice it's the derivative with respect to x, and these are x's, and so I can go ahead and take that derivative. So I'm talking x's and y's because that's what we see most often, but we will get into some other variables, especially when we talk about related rates. So anytime the variables match, we just do a derivative as normal. Now remember, I could think of this as the chain rule, but if I did the derivative of the inside, the derivative of x is just 1. So I could write it, but there's no need to. The issue comes when our variables don't match. So I'm taking derivative with respect to x of some function y. Now y is a function of x, I just don't know what it is. And I can't really do this and just make up something, but I'm going to show you. So y is some function of x. I don't know what, but let's pretend. So let's pretend y is this function of x. That's what I mean. It means it's more complicated than just 1x to the first. It's some function of x. So if I wanted to take the derivative of y cubed, it would be taking the derivative of this function cubed. And if I asked you to do that, because of your previous work, you would know right away, I'm sure, that you need the chain rule. So we would bring down our power, we would leave the inside alone, subtract 1 from the power, and then multiply by the derivative of the inside. That's going to be our focus here. Just because it doesn't blatantly look like some function of x, y is a function of x, and we have to remember the chain rule to multiply by the derivative of the inside. So let's put our pieces back together. The 3 is there, This was y. So 3y, it's now squared. And then what is that other piece? It's dy dx. And so that's what's going to happen even when we don't have a pretend function that we're saying y must equal, is we're just going to get this answer in red. So I take the derivative as usual. It's a power function, so I'll bring down the power, subtract 1 from the power. But then because y is some function of x, I have to remember to multiply by that derivative of that inside function of x named y. Now as we get into this, you might see in your book that they use y prime. Of course y prime and dy dx are the same, and you are welcome to use either one. From a teaching standpoint, I have students who misinterpret their prime on their y when it's mixed in with so many other powers of y, which we'll see, as a y to the first or various things, whereas dy dx sticks out like a sore thumb. So I will continue to use dy dx even though it is a little bit more writing, because you can't miss it or mix it up with other powers of y like you might with the y prime. Okay, so let's look at one where we have some of both. We have an x, but we also have a y. We can go term by term as usual. If we get to a variable that matches, we do usual derivatives. If we get to a y, which is actually a function of x, we're going to have to remember that chain rule. So the derivative of x is 1. The derivative of 3y is 3 times the derivative of the inside. Right now we're just doing expressions. This will be just a small part of a full problem, which you'll get to see in a couple pages, but just so we can warm up of what this looks like. So this one, the last one on this page that we're really going to have to focus on, has x times y squared. Well, remember, x is obviously a function of x, but y is also a function of x. That's what we have to keep reminding ourselves. So this is actually two functions of x being multiplied together. So we're going to have to be really careful and catch that this is the product rule. Because again, I don't see x's multiplied together just kind of alerting me to this, but y really is a function of x. And so it really is the product of two functions of x. So I'm going to have to apply that product rule. And then as I am, I will also have to remember when I get to the y part and taking its derivative to use this implicit differentiation. So here I'm just going to first write the product rule, then deal with the implicit. So we have first times derivative of the second plus second times derivative of the first. Now I'm going back to do those little baby derivatives that popped up. When I get here to the y squared, I'm going to take the derivative as usual, but then I must remember times the derivative of the inside. So the derivative of y squared is 2y, and then we'll have this times dy dx. And then over there, I don't need to write the one for derivative of x, but I wanted to show you I had done each piece. So we're going to kind of see what a full problem looks like and how we will approach it on the next page. So this is how we will attack one of these problems. We'll have an equation, not just an expression like we did last time. And we will take the derivative of both sides of the equation. Again, you don't really think about it, but you've been doing that all along. But your left side was just y, and its derivative was y prime, or dy dx. So you really were doing it. Then when we do that, because of implicit differentiation, we are going to have dy dx's pop up. And so then we need to gather all of them together and solve to get dy dx by itself. So a really common mistake that students make with this is they are so used to writing y prime equals that they'll have an equation and then an additional y prime equals on the side. So as we actually look at one, I'll talk to you about that and hopefully prevent that. The y prime or dy dx comes up as part of you taking derivatives implicitly, and then you have to solve for it. It's not already y prime equals. So most of these answers are going to be kind of crazy fractions that could, but don't always, involve both x's and y's. If we can't get the regular equation to be just y equals with x's on one side, it makes sense that we may not be able to get the derivative to just have x's in it as well. So when we gather everything that has a dy dx and then divide it off, that's why we're going to get that fractional look a lot of times. And so something, I want you to understand why this is happening, and we've already talked about that a few times. It's the chain rule. But when it really boils down to it, what are you doing? Anytime you take the derivative of a y, or whatever your output function that's a function of another variable is, you multiply by dy dx. So you do the derivative like usual, and then you multiply by dy dx. The y of that, why, is the chain rule, but in practicality, what do I have to do, Professor Palm, to get these right? Multiply by dy dx anytime you take the derivative of a y. So here is what a real problem will look like. Notice that I've got y's and x's mingled together, and then I'm asked to find dy dx. I don't have any dy dx's yet. When I go to take the derivative, they will come up. So the first step is to take the derivative of both sides with respect to x. Okay, so I've taken d dx of the left-hand side and d dx of the right-hand side. Then within each of those sides, I can go term by term, taking those derivatives. And so we'll have, anytime we get to a y, we're going to start doing the derivative as usual, and then remember the chain rule dy dx. Anytime we get to an x, we do it as usual. So 3y squared dy dx plus 2y times dy dx minus 5 normal derivative dy dx. And then this is just an x. So just normal derivative, 2x. On the right-hand side, don't forget about that right-hand side. The derivative of a constant is 0, and that hasn't changed. So I have 3 terms that have dy dx in them. I need to gather those dy dx's because I want dy dx equals. I want a single dy dx equals, and that's why we're going to have to use factoring. The other thing I accomplished in this step is I have to isolate all the stuff with dy dx has to be on one side, and anything that doesn't have it has to be on the other side. So I moved the 2x over and factored out the dy dx from all terms that had it that were left on the left-hand side. Lastly, I divide to get dy dx completely by itself. Okay, so what I have done is divided both sides by this whole quantity that's getting multiplied by dy dx, and that ends up giving me 2x over 3y squared plus 2y minus 5. That's what a lot of your answers are going to look like. Again, they won't always have both x's and y's, so don't think you're wrong if you only have one of those two variables, but they often will, and they will often be crazy looking fractions like this. So just to show you, even though these are not necessarily functions, they're relations, because this would not pass the vertical line test, right, for a function. It still does make a cool graph, and a lot of these are really interesting. But it's still, the derivative still represents the slope of the tangent line. So the derivative evaluated at a point is still the slope of the tangent line at that point, and I just wanted to show you that that was the case. So if I pick a couple nice points that are easy to identify on this graph, I want to show you that it makes sense that that is the slope. So if our point was 1, 1 here, and we replace all x's with 1 and all y's with 1 just because it happened to be 1, 1, and work that out, we get 2 divided by 0, which is actually undefined. But what does that mean in terms of a slope? It means it would be a vertical line, right? A vertical line has an undefined slope. So that does actually check out. That is what the tangent line would look like there. As one more example, if we use the point 2, 0, now we're going to have to be more careful about which place we plug in the x and the y. So the 2 will go for the x's and the 0 will go for the y's. Now we get negative 4/5. If we sketch in the tangent line here, that seems pretty reasonable. It is definitely negative, and it looks like it's close to a slope of -1. Negative 4/5 is pretty close to -1 there. And so you can see it still represents slopes of tangent lines, even if these are these crazy looking functions or relations instead. Okay, so let's look at another example of a full problem, and you're going to see that other functions that we've talked about knowing how to take derivatives of, all those can still pop up. It's just that we also have to use this implicit differentiation. So I'll start by taking the derivative of both sides of this equation. Okay, so on the left-hand side, the 16 is a constant that stays. The derivative of e to the y is itself times the derivative of its exponent. Well, its exponent is a function of y, and its derivative is dy dx. On the right-hand side, I'll go term by term. If I have x's, I do it like usual, so that's just the power rule, 4x cubed. When I get to a term that involves a y, I start like usual using the appropriate rule, but then I have to remember to multiply by the derivative of the inside, which our inside is y. We don't know what that function is because we can't easily solve this for y, but whatever it is, its derivative is dy dx. So now you'll see I have two dy dx's floating around. I need to gather them on one side and then factor so that I have just one of them. Since this side only has dy dx's, I'm going to move the dy dx's to the left and things without it to the right. So one thing that you're going to have to be careful about when you're doing this is those sign changes. Since that was a negative 3y squared, then of course when I move it over, I will be adding the 3y squared dy dx to both sides. So that's a place for easy mistakes that you should keep an eye on. Now that I have all my dy dx terms on the same side, I will factor out that common factor dy dx, and then in the next step divide. Okay, so there we factored, and then I can divide both sides, and finally just cleaned up, I have my derivative. Again, I'm used to that fractional form. I'm okay with the fact that it has both x's and y's. So for that reason, when these questions ask us for either a slope of the tangent line or evaluating the derivative at a point or a full equation of a tangent line, they're going to have to give me both the x and the y. So even though it looks like, oh goodness, that's going to be harder because I'm plugging in x's and y's, they will have given us both. So that's what we're going to do. Remember, with this notation, we draw a line and put the point next to it to say we're evaluating it at a point. So this means the derivative evaluated at the point 2, 0. I've got to be careful to put 2's in for x's and 0's in for y's. And then I just evaluate. Now be careful, e to the 0 is 1. So while the second term here is 0, e to the 0 is 1, and 16 times 1 is 16. So the answer that we get here is 2. Now all it said was evaluate the derivative at that point, but we now know from looking at that last example that if we were to graph this relationship and then look at the point 2, 0, we would see that the tangent line that rides alongside and does not cross through it would have a slope of 2, and that's what that means. Okay, so I'd like you to give one a try now. We really are just taking derivatives term by term. When they are x's, we do what we always do. When they are y's, we need to remember to multiply by dy dx. Then it's algebra from there, trying to get dy dx by itself by factoring and then dividing. So give it a shot, press pause, and then we'll check it out. Okay, I hope that you tried it on your own. Nothing explodes if you get it wrong. But if you never practice on your own, then things will kind of explode on the test. So I hope that you did. So we have this x squared minus 4y cubed equals ln of y. This is the first time we're seeing an ln, but we know how to deal with ln because we have all our derivative rules down from earlier units. So the first thing that we need to do is go term by term, taking that derivative. And so I get 2x minus 12y squared dy dx. On the right-hand side, the derivative of ln of something is 1 over the inside times the derivative of the inside. Well, the derivative of the inside is dy dx. So here we have 1 over y dy dx. I need to gather my two terms that have dy dx. Since this side only had dy dx's and the other was a mixture, I chose to move this way this time just to have less work. And so I've moved and changed the sign appropriately so that all terms with dy dx are together. Then I will factor the dy dx out, and to get it completely by itself, to have an answer that we're used to, like y prime equals or dy dx equals, I will divide. So again, notice what is not here is a y prime equals. This is a really common mistake that students make. The y prime or dy dx, they're interchangeable, pops up when you go term by term and take derivatives. It's in there. That's what you're solving for. So in a similar vein, I often will have to write a note that says, what are you solving for? So if you forget the whole point of implicit and you forget that whenever you take the derivative of y, you need a dy dx, you will have nothing to solve for. Because if those were missing, what are you doing? The whole point of this is to solve for dy dx. It's not over here. It pops up when you do it, and then you have to gather them and factor and divide. And so then we're often, again, asked to evaluate it at a point, but they'll always give me both the x and the y, and I just have to be careful to plug them into the right places. When I replace x's with 2's and y's with 1, in this, I get 4 over 13. So in your homework, you can expect like a part A and then a part B evaluating it at a point. Okay, this one is one of the most in-depth ones, and so we're going to kind of work on it together. Often on a test, I will give a smaller version of it, where instead of finding multiple equations of the tangent lines, we're just doing one of them. So we'll talk about that. But what's different is all these S's here. Find the equations of the tangent lines at the points where this happens. So there's a couple things that are going on. First of all, they're saying there's multiple points, and we need to look into that using the value they gave us of x equals -8. Secondly, anything doing with a tangent line, I'm going to need the slope of the tangent line, which means I'm going to need the derivative. So the order that we do those two things in doesn't really matter. I'm going to kind of split my page and do both of them. So just to show you what, why all the S's, I'll actually start with the points there. So what does it mean by the points where x is -8? So this is actually going to just turn out to a simple factoring problem. I literally let x in that equation that I had be -8. Be careful because there was a minus. So I really have y squared plus 8y plus 12 equals 0. And there are multiple places where this happens. And I'm finding the y's that go with it, because again, these are not functions. They won't necessarily pass that vertical line test. You saw a picture of one, but it is a relationship. And so this is just factoring. It's begging you to factor it, right? So I need two numbers that multiply to 12, add to 8. I'm thinking 6 and 2. And then I would set each factor equal to 0 and solve, and I would get -6 and -2. What that means is that there are 2 points where our x's are -8. And these are our 2 points. So we're going to revisit that when we get there on our next page. But the other thing that we need to be able to tackle this is the fact that we're talking equations of tangent lines. We need a slope of a tangent line, so we definitely need a derivative. And again, it's not going to be easy for me to get y by itself on one side to do derivatives how we have been doing them in the past, and so I'm going to have to use implicit differentiation. While I can't get y by itself to see what its function of x is, it is some function of x, and so I have to remember the chain rule. Okay, so I'm taking the derivative of each side, and when I get to y's, remembering dy dx. Now, we're going to have to be careful. Remember that product rule warm-up? It's right here. There's our product rule right there. So the other thing we're going to have to be careful about is there's a minus sign in front of it. So we're going to get two terms out of this, and that minus will affect both. So I encourage you to use a parentheses. So we have first times derivative of the second plus second times derivative of the first. Now as I finish this out, the derivative of 12 is 0, and the derivative of 0 is 0. So remember that you have two sides, that you have an equation there, and now I'll go back and fix that negative, but I had to be careful because I get two terms out of that, and a negative in front affects both of them. So when I distribute, I now have a minus y. So I'm going to group these dy dx terms together, move the y over to get it, since it doesn't have a dy dx separate. And then lastly, to get dy dx totally by itself, I am dividing both sides by 2y minus x. Okay, so we have the first two building blocks that we need to solve this. Ultimately, we are trying to write equations of tangent lines at these two places. But now we have everything we need. Every time we write an equation of a line, we need a point and a slope. We have our points. We can find our slope. That's definitely not a slope, but when I plug these numbers into it, it will be. We can find our slope by plugging our points in. So this is a two-part question. There's going to be one equation of the tangent line for one point, and then separately, I'm going to find the equation of the tangent line for the other point. So I have that here. I've again split my page because I'm talking about two different points. And as a reminder, here's what our derivative is. So I know the point. The next thing I would need is the slope. And so I need to take my derivative and evaluate it at this point. So I'm plugging in -8 for x and -6 for y to see what my slope is. And we end up getting 3/2 on this equation. I now have a point, -8, -6, and a slope 3/2, and I can use my favorite line writing method to write the equation. So you are welcome to use y equals mx plus b and solve for b. If you remember to go back to writing the equation as your answer, you know my favorite way is this way, but you are welcome to use either one. So y minus your y equals m times x minus your x, and then you're distributing and then getting the y equals form to end up in y equals mx plus b form. Then you can see we're just redoing that. We still have the same derivative, but we're evaluating it at a different point to get the slope at that point, because it will be different, and replacing our x's with -8, our y's with -2, and we get a slope of -1/2, and now we are using this point and its corresponding slope to write the equation of the tangent line. So that one does end up being involved in that you're kind of doing double the work in some places, but the point being that these are not functions, they may not pass a vertical line test, and that there can be multiple places where you have one given x value, and it was just a factoring problem for finding out where that happened with multiple y values. And then, yeah, it's more work than some other problems, but think of it as two little problems then. We were just having to plug in to get the slope, and we had a point to write the equation of the tangent line. Okay, so I want to look at a couple more that kind of pick up the level a little bit so that you can have them in your toolbox. And they do take quite a bit writing, and I don't want you just watching me writing. So I have pre-written it, but I do want to explain it step by step for you. So we always are going to start by taking the derivative of both sides, but I know that to do that, I'm going to need that chain rule, that extended power rule form, and so writing it with a power instead of a root will be helpful for that. So I'm going to take the derivative of my first term. That requires the chain rule. Bring down the power, subtract 1 from the power, leaving the inside alone, and then times the derivative of the inside. So the derivative of the inside, derivative of 21 is 0. Derivative of y squared is 2y dy dx because of this implicit differentiation. And it does so happen that those 2's will cancel. Then the derivative of the 3x, the x cubed part is just regular 3x squared, and then derivatives of constants are 0. Then we would group our dy dx terms together, and this is one big one. I just cleaned it up. The y was already in the top. This negative 1/2 means that that quantity should be in the bottom because of the negative and under a root because of the 1/2 power. And then we moved our 3x squared over to the right because it did not have a dy dx in it. And so as our last step, we will divide both sides by this y times, or y over the square root of 21 plus y squared. But remember, division by a fraction is the same thing as multiplying by its reciprocal. And so I could write it that way. All right? So that is my derivative. And we did have kind of a chain rule mixed in with this implicit. So that's kind of the new piece. And I wanted to show you one. And then we're back to just plugging numbers into it. So they told us to evaluate it at 4, 2. That means in this answer you got for the derivative, replace all x's with 4, all y's with 2. And when you do that, you can pause it and check it and see that you get 120. Okay, now this one is probably the most algebra heavy. So I want to make sure there's something key here, and it really is algebra, not calculus, but you need the review of it, that the only way you can solve is to do this distributing that we're going to look at. So I am going to need the chain rule because I have an inside and outside function, and I do have y's mingled in here, so anytime I take the derivative of a y, I will need dy dx. So first, as always, we take the derivative of both sides of the equation, and now let's see what that looks like. So we bring down our power, leave the inside alone, subtract 1 from the power, then multiply by the derivative of the inside. I kind of slowed down a little bit here and didn't actually take it yet, but said I was going to. And then on the right-hand side, the derivative of 3y cubed, I take the derivative as usual with the power rule, 9y squared, but then times dy dx, because y is a function of x. That is that chain rule, that implicit differentiation. And then the derivative of the constant 8 is 0. So that was just me applying the chain rule. Now I'm going back to evaluate this little ddx that popped up, and that's where on the left-hand side my implicit differentiation is going to show up. So I'm just recopying the part that was already done, and now I'm going term by term to take that derivative of our inside. The derivative of 2x is 2. The derivative of negative 3y is negative 3 times dy dx. Because it was a y I was taking derivative of, and y is really a function of x. And now this is where we have to be careful. This is what's different than previous problems. So I have to isolate dy dx. It is, well, one of them is over here, but the other one is stuck inside this parentheses, and that parentheses is being multiplied by this entire thing. So while that might be uglier than you're used to seeing, this is one big factor being multiplied into this parentheses with 2 terms. So what we have to do is to distribute it. I'm treating it as one enormous chunk, and I am distributing it to each term. So that's what's new here. That's what we're focusing on here. We've done problems where we needed the chain rule already. But I absolutely must treat this as one big chunk and distribute it in here so that I get 2 separate terms where dy dx is free to move around and come over to join its friend dy dx on this side. Okay? So just to keep things pretty, I wrote it in a little bit different order than normal, but here is me multiplying the 2 with that enormous chunk, and then I'll clean it up in a second. If you can jump straight to the next step, that's fine. And now here with the distributing, I am multiplying the 3 dy dx by that entire chunk. Okay, so that is down here. Now I'm cleaning it up a little bit. The 2 times the 4 is just 8. The 3 times the 4 is just 12. And so now I have two terms, one that does not have any dy dx's in it, and one that does, that I want to gather on the other side with my other dy dx. And I'm able to do that now. So that is our next step, is to add the term from the big ugly term, but term nonetheless, from the left-hand side over to the right-hand side to join the other dy dx. And then in our next step, we will factor that dy dx out to solve. All right, so this is where we were. We had moved everything over, and then we factored dy dx out. And now to get dy dx by itself, that's our y prime, that's our derivative that we've been looking for this whole time, all we need to do is divide both sides by this enormous quantity that was being multiplied by dy dx. So as beautiful as I know you think this is the derivative. And so it's that quantity over what we had on the right-hand side with lots of x's and y's mixed in. And as with any other problem, if we are asked to evaluate it at a certain point, we simply plug in. Now this one is easier because x and y are the same, so you don't have to think too hard to keep them straight. But all your x's will be 2's and your y's will be 2. If those numbers aren't the same, be more careful with your plugging in. And as we plug in and evaluate, you can pause and work it out and make sure you get the same thing. We should get 16 over 15. So I did a whole lot of practice here because I wanted to show you kind of everything that could possibly come up, that you could have an e built into this, you could have an ln show up in this, you could have the chain rule show up in this, or like in this example, the chain rule where the dy dx part is here and you must distribute, and it's just algebra, but a review of that for you, in order to get that dy dx free flowing as its own term, that it could then go join other terms with dy dx for us to solve. Okay? So this will take some practice. Just always remember times dy dx. Anytime you take the derivative of y, do the derivative like usual and then times dy dx. And what you'll see in our next section related to rates, we will have to apply this to that. So you really want to make sure you practice and get this down very solid, because we are going to be using it as we go forward for word problems. I know you're excited.